Hi, this is Dave Johnson with another edition of Math Off Topics. Today I want to derive Stirling's formula, which was the formula that I used to find 1 million factorial in another video. And in order to do that, I'm going to use the factorial property of the gamma function, which I also derived in another video. And in this video, I'm going to use that factorial property along with something called Laplace's method. We're going to talk a bit about Laplace's method in this video. So let's get into it. So here's the factorial property, which just says that n factorial can be represented by this integral, and that came from the gamma function. The Laplace's method, which I want to talk more about, but let me just mention it here. It's one of the givens that we're going to use. And then what we're trying to do is find Stirling's formula. Again, this is the formula that I used in another video to find the 1 million factorial, but I had just written it down. I didn't derive it. So here we're going to derive it. So let's spend a little bit of time and talk about Laplace's method. Now, Laplace was a famous mathematician. He contributed a great deal to mathematics. But one of the things that he did, which doesn't get much attention, is this so-called Laplace's method. And what it is really is he used it to find approximations to integrals of this form. So where the integrand is e raised to something where this m is a large number times some function f, which has some properties we'll talk about. And that approximation became the square root of this expression, 2 pi over m times the absolute value of the second derivative of evaluated at x naught times e raised to our large number times the original function f evaluated at x naught, where x naught is the local maximum of f. So if you can write the integral in this form, in other words, if you can find an f of x from whatever the integral is that you're trying to approximate that has a local maximum, and by local maximum we mean that the second derivative evaluated at that critical point is negative, and where m is large enough, and here he's imagining that it becomes exactly correct if m goes to infinity. So if you can do all of that, then you can use this method to approximate this integral. So we have to make some transformations first. We're going to start with this, and I've rewritten it down here. So n factorial is the integral from 0 to infinity t to the n e to the negative t dt. And now you can notice that this isn't quite right from what we're trying to get. We'd like this whole thing to be an exponential, but it's t to the n times an exponential. So it turns out there's a simple way to get there. So if we rewrite t to the n in the following way, so t to the n is equal to e raised to the ln of t to the n. That's just a simple log property. And then rewrite that as e to the n ln t. Now we can replace the t to the n. So integral 0 to infinity e to the ln or n ln t times e to the negative t dt. But now we can combine these exponentials in the integral. So we get the integral from 0 to infinity of e to the n ln t minus t dt. Now we're almost there. This isn't quite there yet because notice we have e to the big number times f of x. And here we have our big number times ln t, but we don't have the big number times this other part here. So we need to be able to factor out the n, but the convenient way to do that is going to be to do a substitution. So we're going to let t equal to nx. And now we make that substitution in the integral. If, let's look at the limits first. If t is 0, then x is 0. So that limit doesn't change. If t is infinity, x is going to have to be infinity for positive n. So that limit doesn't change. And we also have to worry about our dt. So dt is equal to n dx. N is a constant, and our x is going to be our new variable of integration. So now we can substitute in. So n factorial is equal to the integral from 0 to infinity, e to the n ln. Now t gets replaced with nx, and notice we're looking over here. And then minus t is, so minus nx. And then of course our dt becomes n dx. Now we're still not quite there. If you think about it, we still need to do a couple more things. So I'm going to rewrite this. I'm going to bring the n out. Go ahead and do that now. So n times the integral from 0 to infinity. I'm going to expand this ln nx, so e to the n ln n plus n ln x minus nx, and then dx. Now this part here, the n ln n, I'm going to write that as e to the n ln n as a separate factor and bring it out of the integral, because that's all constant. So we get n times e to the n ln n times the integral from 0 to infinity e to the n ln x minus nx dx. And we're almost there. So what I want to do now is I want to factor out the n, and then I'll have exactly what we need. So n e to the n ln n times the integral from 0 to infinity e raised to the n times ln x minus x times dx. And let me go ahead and identify the ln x minus x as our f of x. So f of x is ln x minus x. Give myself a little bit more room here. Okay, so far so good. Now we need to, so if you look back at what we need e to the m ln, m f of x, where f of x has a local maximum at x naught and m is large. Well, I think we have that. Here's our large m. I've written it as n, but it's in Laplace's method, that's what he's calling m. And this is our f of x. And so we need to do one more thing. We need to take the derivative here. So f prime of x is equal to 1 over x minus 1. If we set that equal to 0, then that implies that x is equal to 1. And so that's going to be our x naught. And furthermore, let's go ahead and verify that that's the local max. So do the second derivative. So derivative 1 over x is negative 1 over x squared. And since x is 1, then this is clearly negative. So we now have all the conditions of the theorem satisfied. So let's go ahead and copy this expression so I don't have to keep referring back to it. Copy and paste it down here. Let's move it over here. And now our n factorial is equal to the n e to the n ln n times the integral, which is given by this approximation. And so this is approximately true. Okay. Now let's go ahead and rewrite this. This is going to be n times e to the ln of n to the n times, let's go ahead and evaluate what we can. In the square root, we get 2 pi upstairs. Downstairs, m is just our n. And if we plug in x equals 1 into our second derivative, we get -1, but we're taking the absolute value of that. So that's the absolute value of -1, which is, of course, 1, times the e raised to the n times, now if we evaluate our f of x at x naught, which is 1, ln of 1 is 0 minus 1, so we get n times -1 in that exponent. Okay, we're getting closer. So we can write this as n times, now the e raised to the ln of n to the n is just n to the n. And we have the square root of 2 pi over n, and then 1 over e to the n. Or we could write that as e to the negative n. That's probably the better way to write it. Let's do that. So e to the negative n. Okay, but now this, notice we got a square root of n downstairs, we've got an n upstairs, so n divided by the square root of n is the square root of n, and so we can include that inside this radical. And so let me rewrite this as n to the n e to the negative n times the square root of 2 pi n, and that is the formula that we wanted to get. Anyway, I hope you've enjoyed this video, and if so, please like and subscribe, and I'll see you in the next video.